The radio altimeter measures the height of an aircraft above the ground to a very high degree of accuracy. Apart from providing a flight deck display of height above ground level, the radio altimeter has two other important functions. It supplies the Autoland system with the accurate data necessary to carry out Category 2 and Category 3 instrument landing system approaches. This will be covered later in the course as part of autoflight. It also provides height information and rate of change of height to the Ground Proximity Warning System, or GPWS, and is a crucial component of this system. GPWS is also covered later in the course as part of warning and recording. The common abbreviation RADALT is actually short for radio altimeter, not radar altimeter. The type of signal used in a low-level radio altimeter is frequency modulated continuous wave, or FMCW. However, as we do not cover radio propagation theory until a later part of the course, we will have to take a little time now to explain what this is. Traditional radar uses pulse modulation, that is, a short pulse of energy is sent out. The returned echo is received before sending out the next one. The time interval between transmission and reception is measured, then divided by 2 to give the time for a one-way path. Radio waves travel at 300 million meters per second, so the radar can display this time as a distance. This sort of technique has been used for high-level radio altimeters in the past, but is not suitable for the low-level situation, especially where great accuracy is needed. Let's see why. There is a limit to how short it is possible to make the pulse while still packing enough energy into it. A typical value for a high-level radar altimeter was a pulse length of 1/4 of a microsecond, that is, 1/4 of 1/1,000,000th of a second. When you multiply that by the speed of radio waves, which is 300 million meters a second, the result is a pulse 75 meters long, or, since we are using it to measure height, about 250 feet long. This would mean that, as the aircraft descended and eventually reached 125 feet, the leading edge of the returned echo would be received whilst the trailing edge of the transmitted signal was still being sent. This would give us a minimum measurable height of 125 feet. This is no good to us. The Autoland system needs to receive the signal to initiate a flare right down to 10 feet. Pulse radar is not suitable. We therefore have to use a technique called continuous wave. We also have to use two separate aerials, one for transmitting and one for receiving. However, if we have no pulses, how can we measure a time difference? The answer is to use frequency modulation. Frequency modulation means that, although there is a center frequency of 4,300 MHz, this is continuously varied in a constant pattern by 50 MHz either side. A megahertz is 1,000,000 cycles of radio wave per second. Again, these terms will be covered in more detail later in the course. The basic frequency is varied in what is called a sawtooth pattern. It starts at 4,300 MHz, then increases linearly with time up to 4,350, then immediately reverses direction and decreases linearly to 4,250. Then again reverses immediately to increase linearly back to the center frequency of 4,300 MHz again. This is called one cycle of the frequency modulation, and it repeats itself in a continuous pattern. There are 300 of these cycles every second. With this type of modulation, we have a continuously changing characteristic of the transmitted signal, and therefore we have something to compare the received signal against and to measure the time difference. We'll now see how this is done. Consider the transmitted signal at some particular point in its frequency modulated cycle. Let's assume that, on our graph, it's passing 4,300 MHz on an upward slope. The radio wave travels down to the ground and returns sometime later as a received signal, still at 4,300. By this time, the transmitted frequency is higher. Let's say, just by way of an example, that it's now at 4,310 MHz. This 10 MHz frequency difference directly correlates to a radio height. It is measured and displayed as a height on the indicator. If the aircraft remains at this height, this frequency difference remains the same, and the two lines track the graph in parallel like this, with the transmitted signal as the higher one until the frequency reversal in the modulation cycle. During the downward slope of the cycle, the transmitted frequency is still ahead of the received frequency, but as it's a downward going slope, this means that the received frequency is now the higher one. However, the frequency difference remains the same. It is just negative instead of positive now. This is not a problem as long as we measure the absolute value of the difference and ignore its sense. This method of measurement means that we get a dip in the difference frequency when the frequency modulation reverses direction. However, the measurement system is designed to cope with and allow for these dips, so they do not affect its accuracy. Two frequency bands have been allocated for radio and radar altimeters. The first, which is used by all modern FMCW low-level radio altimeters, is from 4,200 to 4,400 MHz. This can also be expressed as 4.2 to 4.4 GHz. These frequencies lie within the SHF, or super high frequency, range of the electromagnetic spectrum. These terms will be explained when you cover radio propagation theory. At present, just remember them. The other band, which is used by pulsed higher altitude radar altimeters, where they still exist, is from 1600 to 1660 MHz. This can be expressed as 1.6 to 1.66 GHz. This lower band lies in the UHF, or ultra-high frequency part of the spectrum. Remember these numbers and bands because they are favourite exam questions. The radio altimeter has an upper operating limit of 2,500 feet and works right down to the ground. The beam is cone-shaped with a longitudinal beam width of 30 degrees either side of the vertical. This means that the aircraft could be pitched up to 30 degrees nose up or 30 degrees nose down, and it would still be possible to receive a usable signal. The lateral beam width is even wider, 60 degrees either side of the vertical. This means that, in theory, the aircraft could be banked to 60 degrees of roll and still receive a usable signal. Clearly, a large airliner is very unlikely to be pitched or rolled to these extremes when less than 2,500 feet from the ground, or, indeed, at any time. There are two basic types of display, one for where the installation is for a standalone radio altimeter, and the other where it is integrated into the Boeing or Airbus Electronic Flight Instrumentation System, or EFIS. We'll start by looking at the basic display which comes with the standalone indicator. In the top left there is a mask which covers the needle when it is not in use. The top end of the display is the upper operating limit of 2,500 feet. As the aircraft descends below that height, the needle emerges. The scale changes in order to allow the full range of 2,500 feet to be shown, but also to allow greatest reading accuracy at low levels, where it most matters. Here, there is only a short space between the 2,500 and 2,000 feet. Between 2,000 and 1,000 feet there are 5 divisions, each representing 200 feet. Between 1,000 and 500 feet there are 5 divisions, each representing 100 feet. However, once below 500 feet, each division represents 20 feet. It is therefore possible to read the instrument to within 10 or even 5 feet in this part of the scale. Note that this is not actually a logarithmic scale. With modern electronics, it is possible to have different scalings at different parts of the dial, but the scale is read linearly over each particular part of the indicator. A failure warning flag is present if the instrument is switched off or if the self-check system detects too low a signal-to-noise ratio. This would make the information unsafe, so the pilot must be warned not to rely on it. The needle is parked behind the mask in the following three cases. Firstly, when the height is above 2,500 feet. Secondly, if the self-check system detects a fault in the transmitted signal. Thirdly, when the altimeter is switched off or has a power failure. A button on the bottom right of the indicator is used for a press-to-test facility. When it is pressed, the height pointer swings rapidly to a known preset value, usually 1,000 feet. This provides a confidence check to the pilots that the equipment is serviceable. The same button can be rotated as well as pressed in order to select a low altitude index to a desired height in order to give warnings such as decision heights. At the top left there is a low altitude warning light which lights up if the aircraft is flown below the pre-selected height. In addition, there is an audio warning. An alert tone commences approximately 100 feet before the decision height, then ceases abruptly on reaching it. Where the display is integrated into an EFIS, it can vary with the manufacturer and the vintage of the electronics. However, a common Boeing format is illustrated here. Below 1,000 feet, the digital readout continues, but the display changes to incorporate a circular white arc, which is graduated in 100-foot increments. The length of the arc reduces in an anti-clockwise direction as height above ground level reduces. The selected decision height is displayed by a magenta-colored marker on the circular white arc. At decision height plus 100 feet, an oral alert chime sounds. At decision height, the magenta marker and white arc will flash and change to yellow and the alert tone ceases. Pressing the DHRST button will cancel the alert chime and the marker flashing, and will also change the decision height displays back to their normal color. Airbus usually show the radar height directly under the attitude display. The height indication changes from green to amber and the numbers increase in size as decision height is reached, also with an audio warning. Between 2,500 feet and 0, the system is accurate to within plus or minus 3% of the indicated height, or 1 foot, whichever is the greater. This means that it is within 3% down to 33 feet, then within 1 foot beneath that. The radio altimeter is required to indicate 0 as the main wheels touch down on the runway. The height difference between the antennae on the fuselage and the bottom of the trailing wheels on the main landing gear bogies at touchdown is known as the residual height. There are 4 basic elements which determine residual height. The first is the aircraft's size. Next is the aircraft's attitude at the point of touchdown. This effect can, to some extent, be mitigated by positioning the radio altimeter antennae at or close to the centre of the aircraft pitch axis, which is the centre of gravity. Thirdly, when an undercarriage oleo leg is airborne, it is not compressed by the aircraft's weight. It therefore extends more than it would on the ground. Finally, in flight, the rear bogie of a multiple bogie undercarriage usually trails lower than it would on the ground. All of these need to be allowed for, and the overall effect is called residual height. In fact, the effect of residual height can be that, when on the ground, the radio altimeter may show a small negative height. The equipment has been adjusted to indicate 0 when the main wheels first touch the runway surface on landing, and therefore when the aircraft is level on the ground, the antenna will be below its calibrated position relative to the aircraft landing attitude. The effect is particularly noticeable with an aircraft such as the Boeing 747, which actually indicates -8 feet when taxiing back in. In addition, the different physical sizes of the aircraft concerned will create differences in cable run length between the avionics bay and the position of the antennae on the underside of the aircraft fuselage. In larger aircraft, this distance may be up to 100 feet, or in a smaller one as little as 6 feet. If compensation for cable length is not applied, an error is generated. As radio altimeters are generally produced by avionics specialist manufacturers, not aircraft manufacturers, they tend to be off-the-shelf items, not customized for any one type. The combination of residual height and cable length is known as aircraft installation delay and is individual to each aircraft type. Let's summarize this lesson. The radio altimeter measures the height of an aircraft above the ground to a very high degree of accuracy. It is also an essential input into AutoLand and the ground proximity warning system. In order to achieve the required high accuracy and minimum range, frequency modulated continuous wave signal is used. This is why it is called a radio altimeter and not a radar altimeter, which is pulsed. The primary frequency band used is 4200 to 4400 MHz, also known as 4.2 to 4.4 GHz. This is in the super high frequency or SHF band. A secondary frequency band, which is only used by high-level pulsed radars, is from 1600 to 1660 MHz, also known as 1.6 to 1.66 GHz. This is in the ultra-high frequency or UHF band. The radio altimeter has an operating range of from 2,500 feet to the ground. The beam is cone-shaped with a longitudinal beam width of 30 degrees either side of vertical, and a lateral beam width of 60 degrees either side of vertical. This gives an operating pitch limit of 30 degrees and an operating bank limit of 60 degrees. The display can either be standalone or integrated into the EFIS. Decision heights can be set, and there is visual and audio warning. The system is highly accurate. The radio altimeter is required to indicate 0 as the rear bogie of the main wheels touches down on the runway. The combination of residual height and cable length is known as aircraft installation delay and is individual to each aircraft type. This concludes the lesson on the radio altimeter.